All right, chapter 4, section 4, day 2, solving quadratics by completing the square. Yesterday, for day 1 of this, we learned how to complete a square, and more importantly, like what is a square that it's talking about. We're not talking about the actual geometric shape, the visual square. We're talking about the name of a polynomial object, namely this guy. This is what we would call a perfect square binomial. So we'll have two terms together, whether added or subtracted, that is parentheses squared. This is what we would call a perfect square polynomial. And we're going to call it a quadratic because one of those terms in this section will be x. And that x squared is what will give us that parabolic quadratic U shape on a coordinate grid. So we're still dealing within the same kind of family of quadratics, that U shape on the coordinate grid. And what we learned in a previous chapter was that this perfect square binomial can be represented by this perfect square trinomial. This is just the distributed version of that multiplication, because when I have a parentheses squared, or anything squared for that matter, it's that something multiplied by itself. And so if I were to distribute and collect like terms, I would get to this look right here. And in reverse, if I wanted to start with this polynomial sentence and factor it back into this parentheses, I would do that little riddle saying like what multiplies together to give me this last value that also adds together to give me this middle value. And that's ultimately where we get these little illustrations right here about how and why we use the completing the square method that we do. We're asking what two things multiply to make the last that also add to make the middle. What we find with perfect square trinomials is that those values are exactly the same. In this case, the two things that multiply to make 9 that also add to make 6 are 3 and 3. In this case, the two things that multiply together to make 49 that also add to make negative 14 are negative 7 and negative 7. And those perfect square trinomials can be rewritten in this factored form. There's that minus 7 that would multiply together to give me the positive 49, but add to give me negative 14. In this case, the positive 3 multiplied by itself would give me positive 9, but also add together to give me positive 6. This is just how it goes back and forth between the factored and unfactored version, right? And yesterday we talked about, okay, well, if I'm given two of the pieces, right, the first two pieces of a trinomial, I can actually fill in the blank purposefully with something like this, where I'll be able to figure out what will complete the square. That's the terminology that we learned. Complete the square so that I can factor this back into this parentheses. Okay, so, and we'll talk about that. We'll apply that today as to why that would be valuable, how that can help me actually solve a quadratic. And again, this is just another technique. So yesterday we learned this two-step technique over here that's in the margin. And again, we're looking for this third term, just like we saw in the examples. We're going to be given two of the items. Our job is to fill in that third blank for the trinomial that will complete the square. And the process basically was this. This coefficient multiplied by the x, so in this case, the plus b, and we saw it in different versions here. But whatever that coefficient is, I'm going to take that value and divide it by 2, or multiply it by a half, or cut it in half, however you want to visualize it. And then I'm going to square that value to figure out what will fill in that blank. And we're going to apply that again a couple of times today, but it's that simple process. Take that middle coefficient, cut it in half, and then square that value. All of that can be done in 2 steps on a calculator. All right, so today we're going to apply that to 2 examples. Kind of going back to what we have seen throughout this chapter, what we will continue to see throughout this chapter, where we're going to be asked to solve a given quadratic using whatever technique. In this case, we're going to use the technique of completing the square. So in both these examples that we'll do today, our job is to solve, meaning we want to get x equals some value, and we're going to use the method of completing the square to do that. Okay, so let's jump to the whiteboard and apply what we need to. So our very first example today, well, for both examples today, we're going to be asked to do a simple task, or at least a simply phrased task, and that's to solve. Now, it's going to also tell you to solve by completing the square. So it's just really telling you, use this technique of completing the square to solve. And so we're going to do exactly what we did yesterday. and apply it to these examples. But then we're going to take it a step further where it's like, okay, well, so what? We have completed the square. We've created this new trinomial. What can we do with that? All right, so our first example, we're given this. X squared minus 16x equals negative 15. So this will look familiar to what we've done in the past several sections. We're given this quadratic. I know it's a quadratic because this x squared is my highest degree piece of this function. And my job here is to get x by itself, technically, right? My end goal, my end game of solving for this, I'm going to get x equals some number of values. All right, now what I mentioned yesterday, it's worth mentioning again, the uniqueness of this section being completing the square, I will get exactly one value. And we're going to talk about how that is solved for in this case. All right, so, or I can get up to 2, I'll get to that in a minute. So I'm going to complete the square in this phrase. And what I'm going to do is I'm going to focus here on the left-hand side, my x squared and x function right here. What I want to do is I want to figure out how to complete the square on this left side of the function so that I make this a perfect square trinomial. Okay, I want to make this left side a perfect square trinomial. And then if I'm going to be completing the square by adding or subtracting some value to this left-hand side, that if I only did it to the left-hand side, that would break the equation. I would weight this side down and nothing over here. So I have to make sure whatever I do to this left-hand side, I also have to do it to the right-hand side because I need to balance the equation. Because if you think of this like a balance, right? If I give the same amount of weight to both sides of the equation, then it still remains balanced. And so when I complete the square here on the left, I need to do the same thing here on the right in order to balance that equation. All right, so let's go through that technique that we learned yesterday. What I'm going to focus on is this middle coefficient that's multiplied by the x, namely this minus 16. All right, now this negative 16, using our technique from yesterday, what I'm going to do with that is I'm going to cut it in half, divide it by 2. In this case, negative 16 divided by 2 is going to give me a negative 8. All right, now that negative 8, what I'm going to do is I'm going to square that value. And in this case, negative 8 squared gives me 64. This is the technique of completing the square. This 64, this positive 64, tells me that's what I need to add here at the back end of this, these two terms right here. If I add that 64 here, I will have created a perfect square trinomial. But again, just to reemphasize this, whatever I do to one side of the equation, I need to balance it on the other side as well. So if I'm going to add 64 here, I need to also add 64 here to make sure I remain in balance. Okay, so that 64 is going to be applied to the left and the right, but let's see what we end up with here. So I have x squared minus 16x. That part has not changed. But to complete this square, I add 64 because now I'm going to be able to factor this into a perfect square, right? Again, just to kind of talk through it, the riddle is what two things multiply to make 64 that also add together to give me a negative 16? Well, 8 and 8 give me 64, but in order to make that negative, it's going to be a negative 8 times a negative 8, and then a negative 8 plus negative 8 will give me this value, and that's where we're going to get that perfect square. So that's how that worked, how that process helped us. And then on the right-hand side of this equation, that negative 15 didn't go anywhere. That negative 15 is still there. But again, in order to balance this equation, whatever I do to the left also has to be done to the right, to both sides of the equation. So I need to add that 64 over here as well. And by doing that again on both sides of this equal sign, what I've just done is I've made sure that this left side of the equation didn't change in its balance compared to this right side of the equation. All right, so what we have just done is completed the square. So we now have this equation. Still balanced because 64 has been added to both sides. It's still balanced. But now what we've done is we've created a perfect square trinomial on the left. And now what we're going to do is we're going to factor that side. And this is going to end up looking a little bit like something that we dealt with in section 1, or rather section section 3, where we were dealing with using the square roots. All right, so if I factor this side, again, just bringing us back to chapter 2, where we were given these polynomials and asked to factor them back into their parentheses, I have this riddle of what two things multiply to make the last that also add to make the middle. Another way to think about this, just scrolling up a little bit so we can kind of see our previous work. Another way to think about this is that this number right here is actually going to take on some significance. This number right here is the answer to that riddle. What two things multiply to make the last that also add together to make the middle? -8 times -8 gives me 64. -8 plus -8 gives me -16. So actually, we've already solved for this riddle, but here is what we'll end up having. We're going to have a parentheses squared. And at the front, we're going to have this x, that x times x, if I were to distribute this, whatever ends up in here, the x times x will get me back to the x squared. So this part will be the same every time. This piece right here is what we needed to figure out in order to turn this perfect square trinomial into its perfect square parentheses. And the answer to the question, what multiplies to make the last that adds to make the middle, was technically the first step in completing the square, that -8. All right, so here is that perfect square. These are the exact equivalent. This is just the factored version. You're going to see why we've done that in just a second. But the equation is still the same. All we've done is we've rearranged this side into its parentheses, or factored it. On the right-hand side, I can actually combine these two terms. -15 and 64 are two numbers that I can combine. And -15 plus 64 is going to give me 49. That can be performed on a calculator. But what we have created, and this should look familiar as far as what we've done so far in this unit. Again, thinking back to what my original task is, my job here is to solve for x. I need to get x by itself. And this will look like something that we've done in section 3 now, where we solved using square roots. Because what I can technically do now, if my job is to get this x by itself, I want to move stuff away from it now. And the reason why I needed it to look like this, as opposed to solving for it in this perfect square trinomial guy right here, these two guys can't combine together. And so even if I were to get the x squared by itself, there would still be an x on the other side of the equation. Even if I were to get that x by itself, there'd be an x squared over on that side of the equation. So there's no way to get x completely by itself equal to a number as this is. That's why we factor it into its perfect square. And now we can get that x by itself. First thing I'd actually want to move here, this squared. If I take the square root of both sides, right? If I take the square root of both sides, right, and this will be familiar to things we've done in the past now, this x minus 8 quantity squared, the whole reason we do this square root is to get rid of that squared. And on the right-hand side, I have the square root of 49. This one is nice and friendly. Unlike in section 1 where I had to reduce or simplify those things, this one will be just a nice friendly whole number. The one thing I do need to remember is that when I take the square root of a positive number, plus or minus can be a result. So my result here will be a plus or minus square root of 49, which many of you will know is 7. Again, the reason why the square root of 49 would be the plus or minus version, if I were to take the positive 7 and square it, I should get back to 49. But also if I take the -7 and square it, I'd have -7 times -7, the negatives cancel, and I get back to positive 49 again. On the left-hand side of this equation, when I square that, the whole reason I took the square root is I'm going to be left with just whatever's inside the parentheses, namely this x minus 8. And so now I have x minus 8 is equal to positive or -7. So technically, I have two equations right here. X minus 8 equals a positive 7, or x minus 8 equals a -7. And at this point, now it's a one-step algebra problem. In both cases, I'm just going to add 8 to both sides, just like we've done algebraically in the past, and I end up with x equals 7 plus 8, or 15. There's one of my solutions. And on this side, when I add 8 over here, 8 plus a -7 gives me positive 1. These are the two solutions to this quadratic. If I were to graph the quadratic I had at the very beginning, these would be the x-intercepts, positive 15 and positive 1. That'd be the two places that U-shape would cross the x-axis. And we solved this using completing the square. All right, let's do one more example. Go through this technique one more time. And you'll see a slight difference. There's going to be one little pre-step we have to do on this next example. But after that, it'll be the same exact thing. All right, last example for section 4. We were given this quadratic, 2x squared plus 20x minus 8 equals 0. All right, so you'll notice that everything has been organized here on the left, but there's also one other difference than what we've been used to so far in this section. Namely, we have a value that is multiplied out front of the x squared. And that's not really conducive to what we need to do. But here's the good news. We can actually factor that out. Why? Because one thing you'll notice with each of these coefficients, each of these terms, 2 can go into each of them. So particularly in this section, if they're asking you to use completing the square, if you ever notice a coefficient in front of the x squared, get rid of it. Okay? And the way you can get rid of it is factoring it out of the whole thing, right? And they're not going to try and throw curveballs at you where it's like something that's not factorable. If they ever throw something like this at you, it's going to be because there is a common factor. So if I divide 2 out of this whole thing, I'm going to be left over with x squared plus 10x and then minus 4. On the right-hand side, I still have the 0. Okay, so now what I can do is I can actually get this 2 and move it to the other side of the equation by dividing both sides by 2. Okay, if I divide both sides by 2, this actually just goes away. So in other words, this was just kind of like a little bit of fluff in this problem where they just throw in this curveball for you just for the sake of making you do this extra pre-step. So if I were to divide both sides of this equation by 2, 0 divided by 2 stays 0. And then 2 just goes away from this left-hand side, and I'm left with the following. X squared plus 10x minus 4 equals 0. All right. So now I have just an x squared. It's still a quadratic just like it was before, but the convenient thing at this point is now I can just do completing the square, where I couldn't have done that when it was 2x squared. All right, so the other thing that's going on here is that I do have this third term. Now this third term is not a perfect square trinomial, okay? It is not a perfect square trinomial because if it were a perfect square trinomial, whatever two things multiplied together to give me this -4 should also add together to give me 10, but that's not the case. So this is not the perfect square trinomial. So what I want to do here is I want to make this look a little bit more like the last problem. I'm going to take this -4, I'm going to move it over to the other side. And the way I do that is by addition. So when I do that, just to make this look a little bit more like the last problem, I'm going to have x squared plus 10x equals, because now I'm moving the 4 to the other side. And when I add the 4 to both sides, so it goes away here on the left, now I have a +4 on the right. And now this should look exactly like the last problem. All right, so at this point, now I'm going to complete the square just like before. I want to figure out what value goes here. Then I'm also going to balance the equation and put on the other side as well. So I balance both sides to the equal sign. And so here's my process. So there's my coefficient, +10. I'm going to take that 10, cut it in half, and I get 5. That will end up being in the factored version. I'm going to take that value and square it to figure out what value will complete the square. And when I square 5, or 5 times 5, I get 25 on the back end. That's the value that I need to add to this side to make this a perfect square trinomial. But in order to balance the equation, I also need to add it over onto the right side of the equation. So my new equation will be x squared plus 10x, and then I'm going to add that 25 to the left-hand side to make a perfect square trinomial on the left. But on the right, that 4 is still there. But in order to balance this equation, I need to add that 25 on the left-hand side as well. Okay. And again, this will be a similar process to the last problem. And so what I can do now at this point is I can factor this back into its parentheses, answering the rule of what two things multiply to make this last term that also add together to make this middle term. Spoiler alert, it will be this, the answer to that first step. So on the left-hand side, I have this factored version, right? I have this binomial that will end up being squared. The answer to this riddle is going to be that +5 in this case. On the right-hand side of the equation, I can combine those two terms just like we did in the last problem. 4 and 25 give me 29. Now, unlike the last problem, this is something I can actually take the square root of, or unlike the last problem, this, when I try and take the square root of it, it's going to give me like a weird answer. Okay, so, but the process at this point, in order to get this x by itself, I want to take the square root of this whole thing, this mess here on the left, and the square root of the right. And when I do that, I'm going to be left with x plus 5. On the right-hand side, I'm going to have plus or minus, but in this case, it doesn't reduce like a friendly number, like in the last problem. And I'm left with 29 under that square root. And this does not reduce or simplify any further. There are no perfect squares that can go into 29. I only know that because 29 is what we call a prime number. Only 29 and 1 will multiply together to make 29 as far as whole numbers go. But typically for this kind of problem, what you will be asked to do is either put it in exact form, or more commonly in big ideas, they're going to ask you to round this answer to the given whatever. That thing might be the 100th place, that might be the 10th place, whatever it might be. But the thing to keep in mind here is that this is going to be positive or minus. So if I were to take the square root of 29, just to kind of show you on a calculator what I would get. If I were to take the square root of 29, I get 5.39-ish. Okay, about 5.4. All right. That 5.4, if I'm asked to round to say the nearest 10th, it's going to be either positive 5.4 or negative 5.4. And so when I have my two equations, right, I'm going to have x plus 5 either equals, I'll round to the nearest 100th actually, 5.39 positive. That's that positive right there. Or my equation, that x plus 5, that thing on the left, that x plus 5 will equal the negative version, which will be the same thing, but it'll be the negative 5.39. And so again, I go through the same process, and both of these versions, I'm going to be subtracting 5 to the other side to get my values. So to finally solve for this guy, x is going to equal, if I subtract 5 from both sides here, it'd be 0.39. And if I were to subtract 5 from this one, I would actually make it more negative, or make it negative 10.39. And these right here will be my two solutions. And even though they're decimals, if I were to graph the original quadratic that I was given, these would be the two places that it crosses the x-axis, thus being my two solutions. And that's how we can solve these using completing the square. All right, I'm going to stop recording.